let's start with some more integration by parts. Specifically, let's look at a couple definite intervals with integration by parts. So let's say we wanted to do the following. The integral from 1 to e cubed of 2x times the natural log of 5x dx. So when I see something like this, well, first of all, when I see something like this, I think, okay, I'm going to have to do integration by parts. It's definitely not a u substitution. You could try letting u equal something, but it's not going to work out. So when I see a definite integral that looks like it's going to be essentially more complicated than just knowing what the antiderivative is, I typically like to do it as an indefinite interval first, meaning I'm going to ignore those limits of integration. Let's first just look at the integral of 2x natural log of 5x dx. So here we're going to do integration by parts. We're going to let u equal. If you ever have if you're doing integration by parts and you have a log thing, that's always going to be your choice for you, or almost always going to be your choice for you. So we're going to let u equal the natural log of 5x. Our dv has to be the rest, which is our 2x dx. Our du is the derivative of the natural log of 5x, which is 1 over 5x times 5, and 5's cancel. And then your v is x squared. So this integral becomes u times v, so x squared times the natural log of 5x, minus the integral of v du, so x squared times 1 over 5x times 5 dx. And then that second integral simplifies really nicely. And this is going to end up equaling x squared times the natural log of 5x minus the integral of, let's see, a 5 cancels and an x cancels. I just have the integral of x. So we're going to end up getting x squared times the natural log of 5x minus x squared over 2. So then, sorry, just one second, there's something in the way here. We need to move. There we go. Okay, cool. So then, after I've done the indefinite integral like that, I go back and say, okay, now if I actually want to calculate my definite integral, the integral from 1 to e cubed of 2x natural log of 5x dx, that's going to equal my antiderivative, x squared times the natural log of 5x minus x squared over 2, and then I'm going to plug in my limits of integration from 1 to e cubed. So I'm going to get, it's kind of gross, but it's fine. E cubed squared times the natural log of 5 times e cubed minus e cubed squared over 2, and then minus 1 squared times the natural log of 5 minus 1 over 2. And I would probably just leave it like that. I suppose you could do a little bit of simplifying. E cubed squared is e to the 6th. The natural log of 5 e cubed. No, I'm just going to leave it as the natural log of 5 e cubed. Minus e to the 6th over 2. And then this would be minus natural log of 5 plus 1/2. But the point is, if I have a complicated integral that's a definite integral, I like to do the antiderivative part first and then go back and, okay, now I'm going to plug my limits of integration. I don't want to have to write from 1 to e cubed throughout this whole process. It just gets a little messy. So that's what I would recommend. Let's look at another example of this. One sec. Go. Sorry, I had something copied and pasted, and now it's not wanting to copy and paste. One moment. There we go. Cool. Bless you. Oh, I think it just keeps, I see the problem. I just keep seeing the same thing because of how things are oriented here. One second. Why are we having problems here? Oh, well, okay. There we go. Sorry, the chat's being. Okay, there's the attendance form. It's there multiple times, I believe. Hopefully you all get a chance to fill that. All right, so let's look at a similar example. Let's look at the integral from 0 to 6 of x squared divided by e to the x. So this one, again, I don't see a good u substitution. Letting u equal x squared isn't really going to help. Letting u equal e to the x, probably not going to help. It's probably integration by parts. And if we rewrite it, it might be a little easier to see that we have x squared times e to the minus x dx. Now, I will point out here, we can kind of integrate this directly in that we could use tabular integration. So I'm going to write my table where u is x squared and dv is e to the negative x. And then all the derivatives are u are 2x, and the derivative of 2x is 2, and the derivative of 2 is 0. My antiderivatives of e to the negative x are negative e to the negative x, and then the antiderivative of that is positive e to the negative x, and the antiderivative of that is negative e to the negative x. And then we go down and to the right. So plus that, minus that, plus that. So then we could write this definite integral as, well, it's just all this. So it's negative x squared times e to the negative x minus 2x times e to the negative x plus negative 2e to the negative x from 0 to 6. And then we can plug in. So we're going to get, plugging in 6, and we get negative 36 e to the negative 6. Minus 12 e to the negative 6, minus 2 e to the negative 6, minus, when I plug in 0, be careful, I don't get all zeros. I do get 0 minus 0 minus 2 times e to the 0, which is just 2. So if I was going to write this out, I'd probably write it as positive 2 minus all this stuff. And that would be my answer. I should mention, for those of you that weren't here on Tuesday or haven't seen the class on Tuesday, we talked about this method of tabular integration that you can use when you have x to a positive integer power times either e to the something, I should say e to a multiple of x, or cosine of a multiple of x, or sine of a multiple of x. So you can't always do this, but when you can, it's usually a pretty powerful tool. It's certainly much better than doing integration by parts twice, which is what you would have to do if you're going to do this the long way. Yeah. So questions about either of these before we move on to, well, it's still the same sort of stuff, just we're going to look at an application from class, or from some classes anyway. All right. People on Zoom, you definitely, you can certainly ask questions if you have them. So let's talk about continuous income and present value. So we should say all the words. So here's the gist. If C of t, the book I think just says C, but C of t is a more normal way of writing it. If C of t represents a continuous income function measured in dollars per year, and the annual rate of inflation is R, then the actual total income over capital T years is given by actual income is just equal to the integral from 0 to t of your continuous income function, dt. That's the easy part. And then the present value, present, can I spell? Yes, the present value is given by the integral from 0 to t of your continuous income function times e to the negative RT dt, which certainly makes the integral harder to calculate. Present value is always kind of one of those things that feels a little bit weird. It's essentially, if you think about how much income you would have made over the years, but it's what you would have to invest now at the current inflation rate to have that much money over that period of time. So let's look at an example that's easy, and then we'll look at one that's a little bit harder. So let's say we had the following. Let's say our continuous income function was $5,000 per year. Or we would just say it's 5,000 really. And then let's say our interest rate is 5%. And let's say the time period we're looking at is 4 years. So the actual income is really easy to calculate here. It's just going to be $20,000. We can still do the integral, but it's going to be very straightforward. So the actual income is going to be the integral from 0 to 4 of this function, which is just 5,000. And that's very straightforward. We anti-differentiate 5,000, we get 5,000 t from 0 to 4. We plug in 4, we plug in 0, and we end up getting $20,000. Which makes sense, right? If you're getting paid $5,000 a year for 4 years, you're going to get $20,000. Okay. Now, the second question here is, what's the present value? And this is where the calculation is going to be a little more complicated. So the present value is going to be the integral of that same thing over the same interval, but now it's going to be your continuous income function, 5,000 times e to the negative. We do have to, it's not going to be e to the negative 5t. It's going to be e to the negative 0.05t, because we have to write our interest, our inflation rate as a decimal. Okay, this one's still not too bad. We know how to integrate e to the something. So this is going to be 5,000 e to the negative 0.05t divided by negative 0.05. Right, whenever you integrate e to the something times t, you just get e to the something times t divided by that coefficient. And this is where I would probably do a little bit of simplifying. 5,000 divided by 0.05 is going to be 100,000. So it's actually going to be negative 100,000. So we're going to get negative 100,000 e to the negative 0.05t from 0 to 4. It's going to end up being negative 100,000 times, so since when I plug in 4, I'm going to get e to the negative 0.05 times 4 is negative 0.2 minus e to the 0 is just 1. And then I guess if I was writing this as an answer, I might do I might rewrite this as negative 100,000 times 1 is positive 100,000 minus 100,000 times e to the negative 0.2. That's your exact answer. This doesn't feel very useful though, right? If I told you that's the present value of your dollars, you're like, great, James, you've told me nothing because I don't know how much money that is. So this is a time where it really is appropriate to get a decimal approximation. If you plug this into a calculator, you're going to get a value that's approximately $18,126.92. So that's how much money you would have to invest now at an inflation rate of 5%, so that over 4 years, it would be equivalent to having that $20,000 of actual income. Okay, let's look at a harder example. Unless there's any questions about this example. All right. So it's not terrible when the what's the word I'm looking for? When the continuous income function is a nice integer, or I mean a constant, I should say. It's a little bit less nice when your income function depends on time. So let's say we have something like this, and this is problem 69 from my textbook from this section, but it's an older textbook, so it might not exactly correlate. Let's say we have the following income function. So income is given by C of t equal to $150,000 plus $75,000 times t for a 4-year period. Okay. So how much money are we actually going to make in actual real dollars? Well, we're going to integrate. We're going to do the integral from 0 to 4 of, now this is where I would definitely encourage you to do some factoring out. Both 150,000 and 75,000 are multiples of 75,000. So I really think it's going to be easier for me to visualize this if I pull out a 75,000, say, okay, it's the integral from 0 to 4 of 2 plus t. And that just, I mean, I know it's not really any different, but it just feels a little easier to work with that. So I would really encourage that if you can see that. So then we're going to integrate. We're going to get 75,000 times 2t plus t squared over 2 from 0 to 4. I'm going to plug in. We're going to get 75,000 times, plugging in 4, I get 8 plus 16 over 2 is also 8, which I wrote 16 for some reason because I was adding them together. Minus, if I plug in 0, I'm going to get 0 plus 0. So I'm going to get 75,000 times 16, which ends up being, what was that? I should be able to do that in my head. $1,200,000. Okay. Now for the more interesting question. What's the present value of that income? Meaning, how much money would you have to invest today to have that much income over the 4 years with the current interest or inflation rate? So now is where things get messy because we're going to do the integral from 0 to 4 of our function, 150,000 plus 75,000 t times e to the, I forgot to say what the interest rate was, or the inflation rate, sorry. Yeah, so present value if the inflation rate is 4%. So we're going to have times e to the negative 0.04 t dt. So couple things. First, I can see from experience that we're going to have to do integration by parts here. So I'm going to kind of leave off the 0 and 4 for a minute and just look at the integral. So let's talk about the indefinite integral. And first and foremost, I'm going to again factor out a 75,000. So I'm going to do 75,000 times the integral. I'm going to ignore the 0 and 4 of 2 plus t times e to the negative 0.04 t. And we might as well do it the long way. You totally could do a tabular method here, but since it's only your variable raised to the first power, you don't really need to use the tabular method. So we're just going to do a regular integration by parts. We're going to let u equal 2 plus t. dv has to be the rest, the e to the negative 0.04 t. Our du is 1 dt. And our v is e to the negative 0.04 t divided by negative 0.04. So when we write this out, we're going to get 75,000 times all of uv minus the integral of v du. So uv, that's going to be 2 plus t times our e to the negative 0.04 t over negative 0.04 minus the integral of v du. I think I can fit it in here. E to the negative 0.04 t divided by negative 0.04 dt. It's a little tight there. Sorry. All right. So then simplifying this, we've got 75,000 times. So I should point out, dividing by 0.04 is like multiplying by 25 0.04 is 4/100ths, which is 1/25. So dividing by 1/25 is like multiplying by 25/1. The reason I just don't want to keep writing this. So I know I'm really multiplying by -25 here. So I really have -25 times 2 is -50. -25 times t is -25t times e to the -0.04t. And then we're going to do the integral of this. So I'm going to get plus the integral of, well, again, dividing by 0.04 is really like multiplying by 25. So it's really 25 e to the -0.04t. So then we're going to get 75,000 times -50 minus 25t times e to the -0.04t. And then the integral of this is going to be minus 25 e to the -0.04t divided by 0.04. Or I should have said, I really should have said plus 25 e to the -0.04t divided by -0.04, but I pulled out minus sign out front. Okay, so that's our integral. And then we can go back and say, all right, if I actually want to calculate the amount, I'm going to take that integral and plug in 0 and 4. And I feel like I could try to squeeze it on this page, but I really would, it'd be hard to read. So let's just use another page. So if I now want to find the actual present value, it's going to be the integral from 0 to 4 of my 150,000 plus 75,000 t 0.04 t dt. Word of advice, just in general, when you're writing out things and you have plus signs and t's, try to do a good job of making sure your t's look different than your plus signs. It's very easy to accidentally mistake one for the other, then things go wrong. So I always try and draw like a t with a little curly bottom there, and the plus sign is very straight, so they look different. So this is going to equal our antiderivative, which is this gross thing here, 75,000 times -50 minus 25t times e to the -0.04t minus 25 times 25, right? Because dividing by 0.04 is 25 times 25 is 625. From 0 to 4. So then we just plug it in and we get 75,000 times, so if I plug in 4, I'm going to get -50 minus 25 times 4. That's -150. E to the negative 0.04 times 4 is 0.16. Minus, if I plug in 4 here, 625 times e to the -0.16. Minus, when I plug in 0, I'm going to get -50 minus 0. So -50. Times e to the 0, that's just 1, minus 625 times e to the 0, which is also just 1. And then I suppose the only simplification I would do here would be to say I have 75,000 times, this is plus 50 plus 625, so that's at 675. And then minus 150 minus 625 is minus 775 e to the -0.16. That's about as nice as I can write the answer without doing anything else. If you do throw this into a calculator, you're going to get approximately $1,094,142.27 approximately. Something to be aware of, just in case you're doing these calculations, like, so if you might not have to do this, some people don't cover this way, but if you are doing these, your present value should always be less than your actual, right? Because you should have to invest less money as it earns interest or it gets inflated to end up with the same amount of money over the same amount of that time. So your present value should always be a lesser value than your actual income, which is kind of interesting. It's weird though, because like when you talk about it as interest, it makes sense. Like you're saying, okay, if I took this amount of money and invested it earning 4% interest over this number of years, it would make sense that I would end up with the $1.2 million. But when we start talking, when they start using the word for inflation, to me it becomes more confusing because I'm like, well, if it's inflation, then is my money worth like less later? And it's still the same idea, but that's not really, it's not the word we're using exactly. So yeah. Would you like to do one more example, or should we move on? Okay. So the next example is very similar, but there's kind of not, they don't really, I mean, you can't really do a lot else other than these kinds of functions. So let's look at this one, which is actually very similar to the question you specifically sent me from your class, but a little bit different. So a pro athlete signs a 3-year deal in which the earnings are given by the continuous income function C of t equal to $400,000 plus 100,000 times t. I kind of like this problem in the context of a pro athlete deal in that it kind of makes sense to be a limited time period, right? Pro athletes do sign contracts that for a certain amount of time and then they expire. So again, actual, and we'll talk about the interest rate in a second. So the actual income is going to be the integral from 0 to 3 of 400,000 plus 100,000 t. And just like before, I really think it's worthwhile to factor out whatever largest factor you can. So I'm going to pull out 100,000 and do the integral from 0 to 3 of 4 plus t. That's way nicer to deal with. That's going to be 100,000 times 4t plus t squared over 2 from 0 to 3. And then plugging in, we're going to get 100,000 times, let's see, 4 times 2 is, so 4 times 3 is 12 plus 3 squared over 2 minus 0 plus 0. So that's going to be 100,000 times, let's see, 12 plus 4.5 is 16.5. So 1,600,000 is going to be $1.65 million. And then, of course, we have the present value. Let's find the present value, assuming that inflation is 6%, which is lower than it actually currently is. So then we would do this calculation, the integral from 0 to 3 of 400,000 plus 100,000 t times e to the negative 0.06 t dt. And I'm going to do this one the same way I did the previous one, except I'm actually going to carry the whole, I'm not going to do the thing where I do the indefinite integral first. I'm going to carry these limits of integration through the whole problem, just to show you kind of how it's kind of terrible that way. So let's do it this way. I should have just started a new page. So this is going to equal, yeah, I suppose you can do it like that. So we're going to let u equal the 400. Why am I doing? Let me do one thing first before I get too carried away here. Let's factor out 100,000 because no one wants to write 400,000 plus 100,000 t. So let's write this as 100,000 times the integral from 0 to 3 of 4 plus t times e to the negative 0.06 t. That's much better. Okay, so now we are going to do our integration by parts. So we're going to let u equal 4 plus t. Our dv is e to the negative 0.06 t dt. Our du is dt. And our v is negative e to the negative 0.06 t over 0.06. Sadly, dividing by 0.06 doesn't come out nicely like you're multiplying by 25. It's like you're multiplying by 100 over 6, which is not a nice fraction. So we're just going to leave it as is. So here's what we're going to get. We're going to get 100,000 times our uv minus the integral of v du. So our uv is 4 plus t times our negative e to the negative 0.06 t divided by 0.06. And then when people leave these limits of integration in, they say, okay, and that part is going to be evaluated from 0 to 3. And then we still have minus the integral of v du, sorry, which is minus e to the negative 0.06t divided by 0.06 times dt. Also from 0 to 3. I guess it's not really that much worse. I just really don't like it. I think it's my personal bias. Maybe it's really not that bad. But I don't. So here's what I don't like to do. I don't want to start plugging things in here and still evaluating this. So I'm gonna just leave this as is and evaluate that and do this integral here. So this is going to be equal to 100,000 times 4 plus t. I might. Well, it's a t, not a 2. Sorry, 4 plus t times our negative e to the negative 0.06 t over 0.06 from 0 to 3. And then doing this here, so we have a minus and minus, which is plus, but then we're going to do the integral of e to the minus 0.06, so we're going to divide by another minus. So it's going to be overall a negative e to the negative 0.06 t divided by 0.06 twice, or squared. Also from 0 to 3. And now we're going to plug in. So plugging in the 3, we're going to get 100,000 times 4 plus 3, which is 7, times e to the negative 0.06 times 3 is, oh, sorry, it's a negative, apologies. 0.06 times 3 is 0.18, so it's going to be e to the negative 0.18 divided by 0.06. Minus, when I plug in 3 here, I'm also going to get e to the negative 0.18 divided by 0.06 squared. And then minus, when I plug in 0, I'm going to get 4 plus 0, so 4 times e to the 0, sorry, negative e to the 0, that's a negative 1 over 0.06. And then minus, when I plug in 0 here, I'm going to get e to the 0, which is 1 over 0.06 squared. How disgusting. Yeah, I really I'm not a fan. So these problems, the numbers are usually not very nice, which is unfortunate. I didn't have to calculate this one out. I do feel like we should know what it is. So let's actually calculate this one just to see what it is. I'm trying to think if there's anything I would do to make this a little easier to input into a calculator. The only thing I can really think of doing would maybe be factoring out one of these 0.06s in the denominator. So I might rewrite this as 100,000 divided by 0.06, and then I'm left with a 7 times, I should say a negative 7 times e to the negative 0.18 minus e to the negative 0.18 divided by 0.06. And then I'm going to distribute the minus as well. So a minus and minus is plus 4, and then minus and minus is plus 1 over 0.06. Is it nice? No, but it's fine. So let's calculate it. Can you guys kind of see this calculator? Yeah, sure. Let's move this over so you can actually see it. So let's see. So I'm going to leave that till the end. So I'm going to do negative 7 times second e to the negative 0.18 minus, where's my e again? E to the negative 0.18 divided by 0.06 plus 4 plus 1 divided by 0.06. Okay, that seems maybe reasonable. Let's figure out the answers and then actually. So we're going to multiply by this and divide by that. So times 100,000 divided by 0.06. Okay, so we're getting a value of, let's see, 1, 2, 3, 4, 5, 6. So $1,497,000, $497,674.99. Maybe they'll round it up to the 5 there. Let's check and see if that makes sense. Yeah, okay, that seems reasonable. Our actual dollars earned was $1,650,000. So this seems like it's lower as it should be, but not like ridiculously lower. So yeah, that seems like it's probably the right answer. It's possible we could have made an error along the way, but that's probably right. Cool. So these questions are they're not super duper hard to integrate, but they are definitely messy and they require attention to detail. But they're always kind of the same. Actual value is integrating the function, and then present value, you are integrating the function times the e to the negative RT. All right. Let's see what times. Okay. Where'd that piece of paper go? I had 4%. Cool. Yeah, I wanted to do that. Cool. Let's do one more specifically integration by parts problem. Then I feel like we should probably start talking about what's coming up next. So let's do this interval, the integral from 1 to 4 of the natural log of 3 plus 2x. So whenever you're integrating the natural log of some linear function of x, you kind of have a couple ways you can go. We could do a u sub first. We could totally let u equal 3 plus 2x and then just integrate the natural log of u. Or we could just do integration by parts straight away. It kind of doesn't matter which way you do it. Let's do it both ways. Kind of either way, I would prefer not to look at those limits of integration from the get-go. So let's first just do integration by parts. So we're going to let u equal the natural log of 3 plus 2x, and our dv has to be dx. Our du is going to be 1 over the stuff times the derivative of the stuff, dx. And our v, this might actually point out why it's not good to do it this way first. We'll see. And our v is equal to x. We're going to find out if this was the right way to do it. I mean, it's not wrong. It just might not be the nicest way to do it. So let's rewrite our integral of the natural log of 3 plus 2x dx as our u times v. So x times the natural log of 3 plus 2x minus the integral of v du. So v du is going to be 2x over 2x plus 3 dx. Okay, so now this is where things are a little bit interesting. There's a couple ways you can integrate this. You could actually do a u sub here, although I don't recommend it. When you have a linear function over a linear function, it really is easier just to do polynomial division. So we're going to say 2x divided by 2x plus 3. So that's going to be 2x divided by 2x plus 3. And how many times does 2x go into 2x? One whole time. 1 times 2x plus 3 is 2x plus 3. We subtract and we get negative 3. So we can rewrite this as the integral of 1 minus 3 over 2x plus 3. That's going to end up being x times natural log of 3 plus 2x minus the antiderivative of 1 is just x, and the antiderivative of 3 over 2x plus 3 is 3 times the natural log of the absolute value of 2x plus 3 divided by 2. Bag was really trying to add to the dramatic effect there. So I'll remind you, I know it's been a little while, but when you anti-differentiate, I'm kind of ignoring the 3, right? The 3 is just acting as a constant multiple. And then the antiderivative of 1 over 2x plus 3 is the natural log of that stuff divided by the coefficient of x. Because if you took the derivative of the natural log of this stuff, you would get 1 over 2x plus 3 times 2, and then the 2's need to cancel. Okay, so then we can actually do the integral, right? The definite integral from 1 to 4 of the natural log of 3 plus 2x dx is equal to this whole hot mess, x natural log of 3 plus 2x. I'm going to distribute the minus sign, minus x minus 3 halves natural log of the absolute value of 2x plus 3 from 1 to 4. And then we're going to plug in. I should point out, you don't actually need these absolute values here because when you plug in 4 and 1, you get a positive result. That doesn't mean you have to drop them though. Like in fact, I would definitely encourage you, unless there's a really good reason to drop your absolute values, you should just keep them for safety's sake. So plugging in 4, I'm going to get 4 times the natural log of 3 plus 8, which is 11, minus 4, minus 3 halves times the natural log of 8 plus 3, which is 11, minus, now when I plug in 1, I'm going to get 1 times the natural log of 3 plus 2, minus 1, minus 3 halves times the natural log of 2 plus 3. And then I feel like I should simplify this just because I do want to do it a different way and compare my answers. So simplifying this a little bit, 4 natural log of 11 and minus 3 halves natural log of 11 both. Let's see, 4 minus 3 halves is 8 halves minus 3 halves. So I have a 5 halves natural log of 11. I have a minus 4 plus 1, so that's a minus 3. And I have a natural log of 5 minus 3 halves natural log of 5. So 1 natural log of 5 minus 3 halves natural log of 5 is a negative 1/2 natural log of 5, but it's minus a negative 1/2 natural log of 5. So it's actually a plus 1/2 natural log of 5. And that's how I would simplify this answer. Okay, let's do it a different way, just because it might be better. It's good to kind of see which way you would want to do this. We're still gonna have to do integration by parts though. So let's look at another way. So let's say for the integral from 1 to 4 of the natural log of 3 plus 2x dx. Before I do anything, I really don't love that 3 plus 2x there. I'm gonna do a u sub. I'm gonna let u equal 3 plus 2x, and my du is gonna be 2 dx. So 1/2 du equals dx. I'm going to rewrite this integral as the integral of the natural log of u, and then my dx is a 1/2 du. And this is where I think it's a really good idea to change my limits of integration if I'm doing a u substitution. So if x equals 1, we're going to get u equal to 3 plus 2 times 1, which is 5. And if x equals 4, u is going to equal 3 plus 2 times 4, which is 11. That's a good sign, right? My previous integral had some 5s and 11s in there, so it seems sensible that my new limits being 5 and 11 probably makes sense. Now, this is where you could either have memorized the antiderivative of natural log of u, or we could do integration by parts. It feel like it comes up just enough that it's probably worth memorizing. We'll still do it, but I will tell you the antiderivative of the natural log of u is going to be u natural log of u minus u. Absolute value? Yeah, absolute. No, we don't have an absolute value. Sorry. Well, let's do it the long way. So here's one of my issues that comes up is that when you do u substitution and then have to do integration by parts, it's kind of terrible because you've already used u. So I'm going to do integration by parts now. I'm going to use a w instead of u, just so I don't get things confused. So I'm going to let w equal the natural log of u. My dw will be 1 over u du. My dv will equal du, and my v will equal u. And now, instead of doing uv minus the integral of v du, I want to do wv minus the integral of v dw, because w is taking on the role of u in this particular iteration. So that's going to equal wv is going to be u natural log of u minus the integral of v dw, which is u times 1 over u du. And again, I still have the limits of integration from 5 to 11. Oh, and I lost something. I lost my 1/2, right? So I should have really a 1/2 times all of this. So then I have 1/2 times u natural log of u from 5 to 11. U times 1 over u is just 1, and the antiderivative of 1 is just u. So then plugging in our limits of integration, we're going to get 1/2 times 11 times the natural log of 11 minus 11 minus, I guess that's, sorry, I should have done the 5 first, apologies. I was kind of doing the top, it's fine either way, really. If I plug in the 5, I'm at minus 5 natural log of 5. No, I'm sorry, I'm doing it in a way that's kind of confusing, I feel like, so let me scratch that and go back. If I do this first part, I get 1/2 times 11 times natural log of 11 minus 5 times natural log of 5. And then minus, if I plug in this, I get 11 minus 5. And now here's the question that's important to answer. Is this the same as my previous answer? Well, let's see. It doesn't exactly look the same. Let's do a little bit of simplifying. So let's see. If I distribute the 1/2, I have 11/2 natural log of 11 minus 5/2 natural log of 5. And then 1/2 times minus 6 is minus 3. Well, that's a good sign in that I do have the minus 3, right? That's matching up. Yeah, are these actually not the same? The way you'd have to really check would be to do that. I really don't want to do that. It's always a pain when you do things differently and they come out slightly differently. They shouldn't be different though, is the problem. So yeah, let me look at one thing really quick here. I feel like I might have made a small error. Let me double check a couple things. Oh, that looks right. Cool. Do that. I don't believe. Oh. Yes. Thank you so much. Good eye. That should be a plus right there, right? Because it's a minus. Yeah. So that's going to make this a plus. That's also going to make this a plus. So that means this is not quite correct. So we actually should have been 4 plus 3/2, which is 8/2 plus 3/2, which is 11/2 times the natural log of 11. And then we have our minus 4 plus 1, which is still a minus 3. And then we have natural log of 5 plus 3/2 is 1 plus 3/2 is 5/2, but that's minus that. So it's minus 5/2. And now they're the same. Thanks, Devin. Save my bacon there. So it shouldn't matter which way you do it, other than one's probably better for each person. Meaning, like, I think this is probably the worst way of doing it. I think it was definitely a little bit simpler of a process to do the U sub first and then have nicer numbers to plug in at the end. But as is with everything, really whatever way feels better to do is what you should do. All right, so here's what's coming up next, probably. Well, no, I definitely have seen it, I think, on both classes, homework assignments. Partial fractions. So let's look at an example. Say I want to find the integral of 2x plus 5 over x squared plus 6x plus 8 dx. And if I saw a problem like this, I certainly first would try and do a u sub. So if I let u equal the denominator, x squared plus 6x plus 8, my du is going to be 2x plus 6 dx, which is so close, but not quite what I have. And there's really no way of making this 2x plus 5 into a 2x plus 6 in a meaningful way. Right? Like I could add 1 and subtract 1, but then I'd have 2x plus 6 over myself and then minus 1 over the stuff. And so I'd still have to deal with this fraction. So this doesn't really work. I don't have a 2x plus 6 times dx. So what we're going to do instead is we're going to break this fraction up into fractions with kind of smaller denominators, for lack of a better word. It's kind of like how if one wanted to, they could break up the fraction, sure, 7/12 as some quantity over 4 plus some quantity over 3. Because you can definitely, in fact, let's actually solve this real quick. If I wanted to write 7/12 as a sum of fractions with smaller denominators that both have 12 as a common denominator, I could say I'm going to multiply everything by 12 here. So then 7 is equal to 3a plus 4b. And although there are actually many solutions to this equation, the one that's easiest to see is that a and b both have to equal 1. So it's definitely true that we can write 7/12 as the fraction 1/4 plus 1/3. And the idea with partial fractions is we're going to take an expression that's a little more complicated, a polynomial or a rational function, and we're going to write this rational function as a sum of two rational functions with less complicated denominators. So there's a couple of things that have to be true to be able to do this. One, we have to be having a rational function, meaning a polynomial divided by another polynomial. Two, the degree on top has to be strictly less than the degree on the bottom. And three, the denominator has to factor. So we're going to rewrite this as the integral of 2x plus 5 over x plus 2 times x plus 4. And now here's the idea. We're going to take this expression and we're going to just ignore the integral symbol for a minute here. We just want to do the partial fraction decomposition. Partial fraction decomposition, which you might have done before decomposition in an algebra or a pre-calculus class. You might not, like it's always something people don't teach, but something sometimes people are like, oh yeah, I've seen that before. So the idea here is that we're going to write this as some constant divided by our first factor of our denominator plus some constant divided by our second factor of our denominator. Because if I wanted to add these together, what would I do? I would multiply this first one by x plus 4 over x plus 4, and the second one by x plus 2 over x plus 2, and then I would add the whole thing. So I'm actually going to show kind of the really long way here this first time, but then we'll do it the shorter way. So what we're really thinking about is, oh, this is really the same as 2x plus 5 over x plus 2 times x plus 4. Just watch this for a moment. It's going to equal a times x plus 4 over x plus 2 times x plus 4 plus b times x plus 2 over x plus 4 times x plus 2. All I did here was multiply this term by x plus 4 over x plus 4 and this term by x plus 2 over x plus 2. So now what do I have? I have two fractions that are equal and the denominators are the same. So what I can really say here is that, okay, 2x over x plus 2 times x plus 4 equals, I can put these together because they have a common denominator now. So what I can really say is 2x plus 5 has to equal a times x plus 4 plus b times x plus 2. I don't really need to write the denominators. I could, right? We could totally say, oh yeah, there's this denominator here, x plus 2 times x plus 4. And there's this denominator here, x plus 2 times x plus 4. But the point of this process is to figure out what a and b are. And I don't need those denominators in there to help me figure out what a and b are going to be. So all I really need is the equation 2x plus 5 equals a times x plus 4 plus b times x plus 2. And I will point out the normal way of getting from here to that actual equation that we want, because that's what we really want, is just to multiply both sides by the common denominator. So I multiply this side by x plus 2 over x plus 4. Sorry, I multiply this side by x plus 2 times x plus 4. I get that. If I multiply this side by x plus 2 times x plus 4, I get a times x plus 4 and b times x plus 2. So there's a couple ways of doing the next part, and oftentimes teachers of this class like to do it the hard way for some reason. The hard way has its merits, and it's definitely useful when things get more complicated. But for now, the way I think you should always do first really is pick what I call our convenient values of x. Meaning, these two things are equal to each other all the time, right? They have to be equal to each other. That's what we want. We're trying to make this always equal. Specifically, they're equal for any value of x you want. And I'm going to pick values of x that make one term disappear. So I'm going to pick a convenient value of x like x equal to -4. So if x is -4, then a times -4 plus 4 is going to go away. So when I do that, on the left-hand side, I get 2 times -4 plus 5. So that's a -8 plus 5. That's a I should really write it out. 2 times -4 plus 5 equal to a times 0 plus b times -4 plus 2, which is negative plus 2. That's going to be a -8 plus 5. So that's going to give me a -3 on the left equal to a -2b on the right. So the b is going to equal 3/2. And then we do the same thing for a. I'm kind of running out of room, so I'm going to go up over here. If I pick x, or if I should say we do the same thing for the other convenient value. I pick -4 to make this part 0. I'm going to pick -2 to make this part 0. So if x equals -2, then I'm going to get 2 times -2 plus 5 equal to a times -2 plus 4 plus b times -2 plus 2, which is 0. So that ends up giving me -4 plus 5, that's 1 equal to 2a. So that a is equal to 1/2. Okay, so here's what we've done. We have just said that a is 1/2, b is -3/2, sorry, positive 3/2, so that you can actually rewrite this fraction as 1/2 over x plus 2 plus 3/2 over x plus 4, which means we can rewrite this integral as the integral of 1/2 over x plus 2 plus 3/2 over x plus 4. And those are both things that we know how to anti-differentiate. We're going to end up getting 1/2 times the natural log of the absolute value of x plus 2 plus 3/2 times the natural log of the absolute value of x plus 4 plus c. So that is the idea of partial fractions, is that you're going to take some complicated rational function and you're going to break it up into smaller pieces that are easier to integrate. Usually the pieces are going to be like a constant over x plus a number, and so the antiderivative is going to be that constant times the natural log of x plus that number. That's very typical in this process. Okay. So let's look at a slightly more complicated example. Follow. So what do I got here? I have got the integral of 3x minus 8 over x cubed minus 4x squared dx. And I'll just point out a u sub does not seem like a good choice here. If I let u equal x cubed minus 4x squared, my derivative is going to have an x squared in it. And I don't have an x squared in the numerator, so it's probably not very likely that things are going to work out. We could try it, but it's not going to work. So if I can't do a u sub, integration by parts is certainly not on the table because they don't even have a mixture, right? It's all just powers of x. The only thing and I can't simplify that in any meaningful way because the denominator has multiple terms. I'm only really left with partial fractions. But again, partial fractions, there really have to be 3 things that are true. Can we factor the denominator? Yeah, we can. Can we, or is the degree on top less than the degree on the bottom? Yes, definitely. And then, oh yeah, well, yes, it's a rational function, right? It's a polynomial divided by another polynomial. So as long as those 3 things are true, we can use partial fractions. So now we're going to have our partial fraction decomposition. So we have 3x minus 8 divided by, if I factor this, it factors as x squared times x minus 4. Now here's an important thing to know. If you have a factor that's raised to a higher power, so here we have x squared, that's a repeated power. when you have a repeated power, you need a fraction for each power that's less than or equal to that power. Meaning, when I write this, I'm going to write this as some constant over x squared plus some constant over x, and then plus some constant over the other factor, x minus 4. So the repeated power means I need a fraction for each power. So I need fraction for each power of x up to the second power. So x to the first, x squared. We'll look at another. We'll do this one, then we'll talk about stuff. So then we're going to do the same sort of thing, right? I'm trying to solve for A, B, and C. Okay, so I'm going to take this equation, 3x minus 8 over x squared times x minus 4 equal to a over x squared plus b over x plus c over x minus 4. And we're going to multiply both sides of this equation by the common denominator, x squared times x minus 4. And when you multiply it by the left piece, the denominators just cancel, right? You're just going to be left with the numerator, which is going to be 3x minus 8. When you multiply it here, the x squareds cancel, and you're going to be left with a times x minus 4. Multiply it here, one of the x's cancels, and you're left with a b times x minus 4. And then finally, when you multiply it here, the x minus 4's cancel, and you're going to be left with a c times x squared. Whenever you do this, all the denominators should cancel. And now, just like last time, we're going to pick convenient values of x. So I'm going to pick x equal to 4. Because x equal to 4 is going to make some things go away. So let's say if I plug in 4, I'm going to have 3 times 4 minus 8 equal to, oops, I don't need parentheses there, sorry, equal to a times 0 plus b times 4 times 0 plus c times 4 squared. You do not have to write the times 0 terms, right? You can just like, yeah, I know they're going to go away, James. You don't need to write them. So I end up getting, let's see, 3 times 4 is 12 minus 8 is 4 equal to 16c. So c is equal to 4 over 16, which is 1/4. Okay, there is one other convenient value of x that's going to make things go away. X equal to 0. So plugging 0 for x, on the left-hand side, you're going to get 0 minus 8. On the right-hand side, you're going to get a times 0 minus 4 plus b times 0 minus 4 plus c times 0 squared. That goes away, that goes away. So I have negative 8 equal to negative 4a. So I have a equal to 2. But now we've run out of convenient values. Right? There's no other value of x that's going to make things become 0. So at this point, you have a couple different options. One option, if you have exactly one thing left to find, is just to pick another value of x. So you could totally pick like x equal to 1, plug in your a value and your c value, and solve for your b value. That's not what I prefer to do. So there's this other method, which is probably what most of your teachers will talk about at some point, which is called, well, some people call it equating coefficients. So if you look at these two equations, 3x minus b equal to a times x minus 4 plus b times x minus 4 plus c times x squared, they're supposed to be the same polynomial, right? We're trying to actually find a and b and c so that this thing here equals that thing there for any value of x. Meaning the coefficients of different powers of x have to be the same. So my usual method here is to say, well, what's the highest power of x on either side? Looks like x squared. So I'm going to say, okay, well, and I'm going to say the amount of x squared on the left has to equal the amount of x squared on the right. If these are going to always be equal, that has to be true. Okay, so looking at this equation, I know it's going to sound like a dumb question. How much x squared is on the left? None. We have 0 x squared on the left. So we're going to say on the left, we have 0 times x squared. And on the right, if I did multiply this out, what would be my coefficient, or what would my x squared terms? Well, I have an a times x minus an a times 4. That's not going to have any x squared. I would have a b times x. That would be a b times x squared. And then I would also have a c times x squared. So if 0x squared equals bx squared plus cx squared, I can conclude that 0 has to equal b plus c. And since I know that c is 1/4, 0 equals b plus 1/4, meaning b equals negative 1/4. Let's check it out. So normally we would just be like, cool, let's go. Well, let's actually look back and see if we have what we think we have. So on the right-hand side here, so now writing this out, I have 2 times x minus 4 plus negative 1/4 times x minus 4 plus c is 1/4 times x squared. And if I actually simplify this out, or expand it out and simplify, I should get 3x minus 8. Let's see if we do. So let's see, I've got 2x minus 8, and then I have a minus 1/4 times, I'm going to multiply this together first and say I have an x squared minus 4x plus a 1/4 x squared. So then let's see, I have a 2x minus 8 minus 1/4 x squared. Minus 1/4 times minus 4x is a plus x, and then a plus 1/4 x squared. The negative 1/4 x squared cancels with the positive 1/4 x squared, and I'm left with a 2x plus x minus 8. Exactly what it was supposed to be, right? So it really, really is true that 2 times x minus 4 plus negative 1/4 times x times x minus 4 plus 1/4 times x squared is equal to 3x minus 8. So now back to the point. That means that we can now write our integral at the integral of 3x minus 8 over x cubed minus 4x squared dx as the integral of our a value over x squared. And our a value, a was 2. Our b value was the positive 1/4? No, the negative 1/4. Negative 1/4 over x, and our c value was 1/4 over x minus 4. That's the whole reason for doing that. And then this becomes not terrible to integrate. So I would maybe do one small thing. I might rewrite this as 2 times x to the negative second. So I've got the integral of 2 times x to the minus 2 minus 1/4 over x plus 1/4 over x minus 4. I'm going to get 2 times x to the minus 1 over minus 1 minus 1/4 natural log of the absolute value of x plus 1/4 natural log of the absolute value of x minus 4 plus c. So just, we're not, oh, sorry. So we're not going to do this next one, but I just want to point out. So for example, if we were going to do the partial fraction decomposition, for the following, I'm going to make it really ugly. For the integral of x cubed plus 2x minus 1 over, how would we go? Yeah, let's say it was x minus 1 to the third times x plus 1 squared. So if I was going to do this problem, which I definitely would not because it's terrible, I would start with this. I'd have x cubed plus 2x minus 1 over x minus 1 cubed times x plus 1 squared. And my partial fraction decomposition is going to have how many pieces? It's going to have 5 pieces. 1, 2, 3 plus 1, 2. So it's going to have a over x minus 1 cubed plus b over x minus 1 squared plus c over x minus 1 plus d over x plus 1 squared plus d over x plus 1. Sorry, one different letters there, apologies. But that's the idea, right? Whenever you have some linear function of x raised or to a repeated power here, you need every lesser power of it as well. So let's look at an example of that. Let's say we want to do the integral of 3x squared plus 1 over x cubed minus 2x squared plus x dx. Now this one, I might do a quick check for a u sub because it seems like it could be plausible. So if I did try u equal to x cubed minus 2x squared plus x, my du is going to be 3x squared minus 4x plus 1. Ah, so close. If I didn't have that, if I just had an extra 4 minus 4x in there, I would be there. But nope, not going to work. But we notice the denominator does certainly factor. So that denominator we can rewrite as x times x squared minus 2x plus 1. And then we can and should factor that further as x minus 1 times x minus 1. Or x minus 1 squared. I should say when you're doing partial fraction decomposition, you need to factor the denominator as much as possible. You have to fully factor it and then group like terms together with their powers. So then we're going to say that this is equal to a over x plus b over x minus 1 squared plus c over x minus 1. And then we're going to multiply both sides by the common denominator. Multiply by x times x minus 1 squared, and you're going to get the following. On the left side, you're just going to get 3x squared plus 1. On the right side, a over x times this will cancel the x, and you'll get a times x minus 1 squared. B over x minus 1 squared times this will cancel the x minus 1 squared, and you're going to get a b times x. And c over x minus 1 times this will cancel one of the x minus 1s, so you get c times x minus 1. And now it's the same sort of process. We're going to pick convenient values like x equal to 0. By the way, the convenient values are just the values that would have made the denominator 0. So x equal to 0 makes this 0, x equal to 1 makes that 0. So that's what we're typically picking. So if I pick x equal to 0, on the left I'm going to get 1. On the right I'm going to get a times negative 1 squared plus 0 plus 0. So I'm going to get a equal to 1. If I pick x equal to 1, I'm going to get 3 times 1 plus 1 on the left, so 4 on the left. I'm going to get a times 0, I'm going to get b times 1, I'm going to get c times 0. So b equals 4. And then I always like to start with the highest power. So I should point out, I've run out of convenient values. Let me actually show you both ways here because I do think it's worthwhile. So one option, and again, this really only is an option if you have one more thing defined. So if you have like 2 more things defined, this is not really a good way of going. But if you have one more thing defined, pick any other number you like that you haven't already picked. I already picked 1 and 0. I would probably either pick -1 or 2. Let's pick 2. So if I plug in x equal to 2, on the left, I'm going to get 3 times 2 squared plus 1. On the right, I'm also going to plug in my a and my b value. So I'm going to get 1 times 2 minus 1 squared plus 4 times 2 plus c times 2 times 2 minus 1. And now I think you can see, pun intended, that we can solve for c because it's the only thing left. So let's say I have 3 times 4, 12 plus 1 is 13, equal to 1 times 1 plus 4 times 2 plus c times 2 times 1. So let's see, 13 minus 9 is 4. 4 is equal to 2c, so 2 is equal to c. That's not my preferred way of doing it, but it totally works. The way I would have done this is I would have looked at the coefficients of x squared. On the left-hand side, the coefficient of x squared is 3. So I have a 3x squared. On the right-hand side, if I multiply this out, I would have an a times x squared. I wouldn't have a b times x squared, but it would have a c times x squared. So then I could say, oh, I know that A is equal to 1. So 3 equals 1 plus, well, C has to be 2. So either way works. I'm more partial to this thing that's called equating coefficients because it's usually, especially if you have more than one more thing to find, it's usually a faster way of doing it. So it's always important to remember that once you've found all the A, B, and C's, you still have to go back and do the integral. Right? I've seen a lot of people like, oh, I found them, I'm done. No, we're not done. You have to finish the thing. So I go back and again, right, I'm just going to be integrating this new thing here. So my integral should be equal to the integral of A over X plus B over X minus 1 squared plus C over X minus 1. Okay. So 2 of these pieces are easy. The 1 over X and the 2 over X minus 1 both end up being natural logs. But the 4 over X minus 1 squared, you could think of doing a U substitution. You could be like, okay, well, we could let U equal X minus 1, du equal dx. So we'd essentially have the integral of 4 over U squared. But the integral of 4u to the minus 2 is just 4u to the minus 1 over minus 1. And we can plug back into u and get a negative 4 over u. Sorry, my 4's and my u's look the same. I know it's terrible. Or a negative 4 over x minus 1. Here's what I really want to say. If I've got 4 over, I don't care about 4. If I've got something over, if I've got divided by x minus 1 squared or x plus 2 squared or x plus 3 squared or x plus a constant to a power, you can just kind of be like, that's going to just be like u to that power. So I'm really thinking of this as 4 times x minus 1 to the negative second. And I'm going to get 4 times, if this is x minus 1 to the minus second, it's going to, antiderivative is going to be x minus 1 to the minus first divided by minus 1. Because when I do the u substitution, I don't have any constant multiple because I just have an x plus a constant there. So I'll say more about that in just one sec. But for that one there, we get that, and then we get 2 times the natural log of the absolute value of x minus 1. Let's see. So I'd probably write this as the natural log of the absolute value of x minus 4 over x minus 1 plus 2 natural log of the absolute value of x minus 1. Let's see. Okay, quick couple things. Yeah, I have enough time to say this. So back to the point of what I was just saying. What if I wanted to find the integral of 1 over x plus 3 to the 6th power? I could do a u sub, but I don't need to. That's the point I want to make. We can write this as the integral of x plus 3 to the negative 6th, and then just kind of use the anti-power rule. The antiderivative of x plus 3 to the negative 6th, well, that's essentially like our u to the negative 6. And the antiderivative is going to be our u to the negative 5th divided by, sorry, it's x plus 3 to the negative 5th divided by negative 5. Plus c. Right? Because what would happen if you took the derivative of this? You would get negative 5 times your stuff to the negative 6 divided by negative 5. And then you have to multiply by the derivative of your stuff, but the derivative of your stuff is just 1. So that's hopefully somewhat clear. So whenever you have to integrate something like x plus 1 over x plus something to a power, you really can just be like, yeah, I'm just gonna be like, that's 1 over u to the 6th, and I know how to deal with that. In a similar way, if you want to integrate 1 over x minus 7 to the 8th power, I'm really just be like, okay, 7, fine, 17. That's going to be the integral of x minus 17 to the negative 8th. And that's just going to be x minus 17 to the negative 7 over negative 7.